So we know that volcanoes are different because the chemistry of the magma is different. That chemistry of the magma is going to be dictated by the plate tectonic setting. So whether we're at a mid-ocean ridge, the plates are coming apart, or at a convergent plate boundary, or maybe we're in the continents and they're rifting, or a hotspot either in oceanic lithosphere or continental lithosphere, we're going to have different parts of the crust lithosphere melting to give us different chemistries that give us different kinds of eruptions. So in this first block, that's a subduction zone, and you've got a volcano. This is within oceanic crust. The next one, you've got a subduction zone, but the magma is rising up into continental crust, so the chemistry is going to be a little different because we've got that continental crust instead of just oceanic crust. In the next block, there is continental crust. Continental crust in these images is this green color, and the oceanic crust is this gray. So the image in the middle, that block, is continental crust that is rifting apart, and magma is rising up into that, eventually making volcanoes within the oceanic crust. The next one would be a hotspot. This would be like Hawaii, that is burning up through oceanic crust. And then the last one is the mid-ocean ridge, where oceanic lithosphere is spreading apart. We have those pillow basalts coming up into the rift zone. Okay. So here is zooming in on the mid-ocean ridge. You've got the asthenosphere melting because of decompression melting. That material comes rising up because it's less dense into that zone where you have all those little normal faults spreading apart the plates, and then magma rising up into the crack. Right in here, the magma is rising up, pillow basalts are forming along the ridge axis. All of that is going to be basalt, right? So at the surface is going to be pillow basalts, and then basaltic dikes, and then below that is that zone of gabbro, where you've got a coarser grain but same chemistry mafic igneous rock down there in the gabbro. So here's the image on the right we saw earlier. There's the pillow basalts, and here's this basalt squishing through the pillows. Here's the Ring of Fire. So the Ring of Fire is the area around the Pacific Ocean where we have subduction zones around the perimeter of the Pacific Ocean. And those are all convergent plate boundaries, mostly between continental and oceanic crusts, as in South America and North America. North America is up there. Oh, wow. That's two maps kind of on top of each other. Looks weird. There is North America up there. Yeah, continental crust, and then the oceanic crust sitting underneath that continental crust and creating those volcanoes. On the other side of the Pacific, mostly we have volcanic island arcs. So the Aleutians, Japan, Philippines, Marianas Trench, all of that down into New Zealand. I just moved my computer for no reason. Those are subduction zones between oceanic and oceanic crust. So the continental crust, mostly on the eastern side, is where the volcanoes are, and on the western side of the Ring of Fire, it's mostly within oceanic crust. Okay, those volcanoes are all because of flux melting. Remember, we've got to figure out a way for that asthenosphere to actually melt. And so we either have that decompression melting at the mid-ocean ridges or the flux melting as the subduction zone carries down volatiles and promotes melting. Okay, so here is East Africa, and that is the East African Rift Zone where, like Ethiopia, other countries are spreading away from the rest of the African plate and creating these really deep, long, skinny lakes, Lake Malawi, Lake Tanganyika, Lake Victoria, those, and volcanism, so like Mount Kilimanjaro is a giant volcano. The chemistry of the melts is going to be kind of varied. There's going to be, depending on if the mantle, if there's partial melting in the mantle, we'll get mafic magmas, and if there's partial melting in the crust, then there's going to be felsic magmas. So the composition really varies. The example here, East African Rift, but then in North America, in the United States, we have the Basin and Range. Basin and Range, not really good to show that map up there, but is like in Nevada, where we have deep basins. We use Death Valley as an example, and then high mountain ranges around these big, deep basins. All right, so this is, pay attention to this. See where the water line is. So here's sea level, boop, 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 boop. And just above sea level is the subaerial, so above the water, shield volcano. So all of this material that below it is all part of this giant volcano that is a shield volcano. These happen in oceanic crust. This one's at a hot spot, and yeah, so they just build really high above sea level. And the volcanoes kind of march away from the hot spot. So right at Hawaii, the magma is new, forming today, and then away from it, the volcanoes get older as we go away. Submarine slumps remove large masses of the volcano. So see the flanks of this volcano? Those like little fault motions here. You have like landslides and chunks of old volcano to slump off of that shield volcano. These can cause really big tsunamis. All right, so that was an oceanic crust. Scoot over to continental hotspots. And this kind of magma is going to be really different. So in this case, we're going to have more felsic material because it's in continental crust. So on the left is all the pyroclastic material that came out of, remember, St. Helens, and then the yellow ones are from Yellowstone, and then the giant one in the middle, that long valley caldera, that's on the edge of the Basin and Range. So calderas, remember, occur when the magma chamber empties and the volcano collapses on itself. So lots and lots of material can come from these volcanoes. The image on the right shows the Columbia River basalts. This is a place where basalt flowed a really long ways, and then to the south of that is the chain of igneous rocks and volcanic rocks that lead up to the end, which would be Yellowstone National Park, and the end of the continental hotspot that starts down there at the McDermott volcanic field 16 million years ago, and then goes up to just less than a million years ago, the volcanism in Yellowstone. Remember I was saying earlier that these calderas, then they're emptied out, but the volcano is still active. So you get little resurgent domes in the volcano. The resurgent domes in the large Yellowstone caldera are on the map. The Sour Creek resurgent dome and then Mallard Lake resurgent dome also. There's little domes within Yellowstone National Park within the caldera. Okay, flood basalt. So that Columbia River basalt, this is one of those. There are these pulses of flood basalts that produce a large volume of basalt and flow a really long ways and cover a lot of land. So that's, and then the image here on the left is a canyon that has been cut down into layer after layer after layer of these basaltic deposits. But they cover the Columbia River area, the Pacific Northwest, and then also, see on this image, there's lots of lava like in northern Russia, right? Okay, another unique, move my face here somewhere. Whoa, where can I put it? I guess that was okay. I'm gonna move it over here. Another unique place is Iceland. So the round map, the globe here on the bottom right, kind of part of the globe, shows Iceland. It's right along the Mid-Atlantic Ridge. And then the bubble up to the left here, that is zoomed in on Iceland, kind of a a geologic map of the area. In the lighter colors are sediments, like soil that has formed on top of the volcanics. The white on here is giant glaciers, but then the red is kind of young volcanics, and orange is a little bit older volcanics. And then those lines that are coming across that are showing like the trace of faults that parallel the mid-ocean ridge. So Iceland is right along the mid-ocean ridge, but it's also a hot spot along the ridge where lots of volcanism occurs at Iceland. So it's being torn apart, basically getting bigger as the North Atlantic gets bigger, as the North American plate separates from the Eurasian plate. So this, well, let me move my face again. My face is too big. I don't know where to put it. Okay, this just summarizes, kind of busy, but it shows a progression of the different volcanic settings that we can find, and then what are the rocks, the whether it's mafic basalts or maybe a more pyroclastic material and a felsic eruption across the different plate tectonic settings. So either we have an island arc, or we have plate divergence is a mid-ocean ridge, or here's some hot spots, then a subduction zone subducting the oceanic crust underneath the continental crust. So different settings for different kinds of magma